never come to conjunction over here. And so that's the reason, one of the reasons that objects can remain stable in these resonances. Pluto's a good example of this. So Pluto's the most famous member of the 3-2 resonance. It actually crosses Neptune's orbit. It's crossed Neptune's orbit for probably 4 billion years, but it's perfectly stable because Neptune's never here when Pluto's over here. And so...
Can I ask you a question about the diagram?
Yeah, sure.
That one?
Yeah.
Are there truly no objects with low eccentricities and semi-major axes of, say, 800 AU, or is it that we only see the ones that are eccentric because they come closer to the sun and we can discover them?
Sorry, you're asking, are there more objects with large semi-major axes?
Say, 500
Yes.
and 0.2.
Oh, down here. That's a really good question. So that'll actually we'll get more into that later. But there are objects, definitely. So you can see some objects like Sedna, 2012 VP113. These are objects that have perihelia of something like 70 to 100 AU. And so they never come anywhere close to the planets now. The odd thing is that they have quite eccentric orbits. We don't believe that objects form on eccentric orbits because they form in the presence of a gas disk, and also if there are collisions, they should actually dissipate any orbital eccentricity. And so it's very strange that these objects don't come near the planets, but they have these huge semi-major axes and large eccentricities. So we don't know really what is populated over here because we can't see them, but it's clear that there's some dynamically unexplained objects over here, and that's actually one of the lines of evidence that there could be a distant planet out there. Now, that's not the only way to get these objects. You could also have perturbations from that occur when the sun still inhabits a birth cluster, a birth stellar cluster. So you have very close stellar encounters, and they can torque these objects away from the planets after they've been scattered by the planets. But yeah. That's a problem with these simulations that I'll get into is we have these models that where we have no discovery bias in our simulations. But in surveys that go out and look for these objects, there's a huge amount of discovery bias because they don't cover the whole sky. And so when you compare simulations with the actual catalog of Kuiper belt objects, you really have to account for the discovery bias, or it'll lead you astray. It'll lead you to incorrect conclusions. And so I'll get more into that later on. But yeah, you're right that there's a huge amount of selection effects for these objects out here. Yeah. Oh, unfortunately, I can't go past this until it finishes 6 orbits around or something. So sorry. No,
you should have asked my question earlier.
no, that's all right.
Actually, while we're waiting, how do you said a tenth of an Earth mass in the Kuiper belt?
Yes.
That's an estimate from some model, right?
That's an estimate from basically looking at the large objects and trying to constrain the size distribution and extrapolating down.
Okay.
Yeah. Okay. Oh, yeah. So So now I want to get into the idea of giant planet migration. So we know that the inner edge of the Kuiper belt, not every object at the inner edge of the Kuiper belt, the part that's closest to Neptune, is stable over the lifetime of the solar system. So it's clear that those scattering objects, for instance, they are not stable. Some of them are on directly planet crossing orbits. They will get ejected eventually. And in the mid-80s, there's this paper by Fernandez and it was a very simple numerical experiment. They just took the giant planets as they are and put down small bodies into planet crossing orbits and watched how the orbits of the giant planets reacted to this population of planetesimals. And what they found is that they behave in different ways. So when they lay down these planets, or these planetesimals, they find that as Neptune interacts with a swarm of planetesimals, it tends to migrate outward over time, away from the sun. Uranus does the same thing. Saturn does the same thing. The reason for that is that, let's say you have an object that's in a crossing orbit with Neptune. Each time it encounters Neptune can either give a little bit of energy to this object or take a little bit of energy away. And it's effectively a flip of the coin which one of those things happens, because it depends on the exact details of the incoming trajectory, and every incoming trajectory is different. And so as an object is undergoing encounters with Neptune, it's effectively randomly walking in orbital energy space. There are 2 end states to this random walk. Either it can be completely ejected onto a hyperbolic orbit away to interstellar space, or Neptune can take enough energy away from this to the point where it starts encountering Uranus, and Uranus begins to exchange energy. Now, if you look at the amount of energy that has to be traversed for each of those end states, it turns out that it takes a lot more energy for Neptune to completely eject an object than to hand it off to Uranus. So in general, when Neptune encounters small bodies, on average, now it does eject some of them, but on average it tends to take small bodies and put them closer to the sun, where they start to feel the effects of Uranus. So if Neptune is taking lots of small objects and moving them closer to the sun, to conserve angular momentum, Neptune has to move outward over time. You can make very similar arguments for how Uranus and Saturn will behave in the presence of small bodies. On the other hand, Jupiter it behaves in the exact opposite manner, because there's no massive interior planet that's interior to Jupiter. And also Jupiter gets the largest energy kicks out of all these objects, so it can eject things the most efficiently. So as a result, Jupiter takes small bodies and puts them far from the sun. And to conserve angular momentum in that process, Jupiter moves in toward the sun a bit. And so when this was first written in the mid-'80s, it didn't get too much attention. It was kind of a curiosity. But it was realized that if you have a bunch of planetesimals scattering out to the giant planets, Jupiter and Saturn should diverge. Their orbits should diverge over time. And same thing with Uranus. And Uranus and Neptune should move outward over time as well. And so the next piece of the puzzle was put in place when in the early 90s, when people tried to look at how Pluto-type orbits would react to this type of migration, the Neptune moving outward over time. And so while Pluto was still in its glory days and was still considered a planet, it had a very odd orbit compared to the rest of the planets. It had an eccentricity much higher than all the other planets, so 0.25. An inclination that was quite high compared to the rest of the planets, 17 degrees. And it also had this curious feature where it was in the 3:2 resonance with Neptune. Its orbital period was 1.5 times the size of Neptune's orbital period. And in 1993, Renu Malhotra ran simulations where she took a disk of test particles and just stuck them just outside Neptune's current orbit, so in the 30 to 35 AU region, and she just forced Neptune to migrate outward from about 20 AU to 30 AU. And what was found, what she found was that when Neptune migrated outward, as Neptune migrates outwards, its resonances have to also migrate outwards. Because as Neptune migrates outwards, its orbital period increases, so therefore its resonances will increase in orbital period as well. And what can happen is objects that are on circular orbits can get swept up in that resonance. And once they're in that resonance, you can think of that as basically a local potential well. They can continue to be confined to that resonance as Neptune moves smoothly outwards. And as a result, what you can see here is that this object is originally not in resonance, but then it gets stuck in the 3:2 resonance and stays there the whole time. Its semi-major axis moves outward with Neptune. But what also happens is as Neptune moves out, its orbital energy increases over time. But its angular momentum stays about the same, and as a result, its eccentricity increases. And it increases to about the same eccentricity that Pluto has today. And this is just a diagram of what happened. This is in a follow-up paper from '95, but basically here's T equals 0, so you have the Sun, Neptune, and Pluto. And then here's T equals today. Neptune just moves steadily out to its modern orbit. The resonance with Neptune moves steadily out as well, and it eventually captures Pluto and carries along with it and excites its orbital energy as Pluto's carried along. So that's just one object, but a consequence of this, if this migration actually occurred, you would expect that lots of objects should be captured into resonance. And not just the 3:2 resonance, but also things like the 2:1 and the 7:4. And so this is from a follow-up paper in '95, and the amazing thing about this paper is I think we knew of maybe 4 or 5 Kuiper belt objects when this paper was written, and that was it. And this paper predicted that there would be these pileups in resonance. And so now, roughly, 25 years later almost, so this predicted that portions of the Kuiper belt are stable over the history of the solar system, and that the Kuiper belt, due to its resonance pileup, should indicate that Neptune moved outward over time. So now when we look at the Kuiper belt, 25 years later, it's not a perfect match, but you can clearly see there's a huge abundance of objects in the 3:2 resonance. There's also a clear spike, although you can't see it as well, in the 2:1 resonance. But again, there's observational bias here. So these objects are roughly 10 AU further from the sun. The brightest of objects falls off as r⁻⁴ from the sun. And so there's actually, this spike is significant. There are not as many in the Plutonio population as in the 2 to 1, but there is a significant number in the 2 to 1 resonance. What is not predicted in this model is this classical belt that is shown here today. But people have done work on that. But clearly there's an abundance of objects caught in resonance with Neptune. And so this is taken as a signature that Neptune has migrated over time. So our general idea is that Neptune has migrated because it has interacted with these small planetesimals that are left over in the outer part of the solar system. So in general, the idea is that after the solar system formed, there was a massive primordial Kuiper belt that extended out to probably roughly 30 AU, and Neptune was much closer to the sun than it is today, maybe at 20, 25 AU. And the inner portion of this belt were on unstable orbits, causing them to interact with Neptune, and that caused Neptune to move out further and eat further into this belt. And so over time, what happened is you have just Neptune continues to eat into this Kuiper belt, this primordial belt, so it gets basically to the edge of the primordial belt, which we think was at 30 AU. The reason we think it's at 30 AU is Neptune has to stop at 30 AU. If that primordial belt extended to 40 or 50 AU, Neptune would just keep eating through it and keep going. And so during this process, the other planets spread apart, and Neptune eats into that primordial belt, and the vast majority of the belt material, as I said, gets transferred in to the inner giant planets, and once it hits Jupiter, it all gets ejected. Now that's for 99.9% of the primordial belt that was there. On the other hand, a small portion gets carried out with Neptune, mostly in its resonances, and the Kuiper belt that we see today is that 10th of a percentile, roughly, that actually survived this whole process and was carried outward with Neptune. So we think that the belt we see today is roughly 100 to 1,000 times less massive than the original belt that was there, that was there when the solar system first formed.
So what's the inner radius of the belt?
So say that again?
There's an inner radius for that belt?
Oh yeah, so this is all a cartoon I made, but the innermost stable semi-major axes are around 37 AU or so. For the modern belt today. That's called the inner belt. There's not much mass there, but there are some stable ones.
Given like where Jupiter and Saturn are.
You're saying the inner radius of the original.
Yeah. So
I'm sorry. Yeah, so that's a matter of debate, but that was actually my next slide.
Okay,
so, Neptune has to move. So if you go back to those Malhotra papers of the early to mid 90s, she found that Neptune had to move by at least 5 to 10 AU to excite Pluto's eccentricity to what we see today. And that generally is, if you want to replicate the orbital distributions that you see trapped in resonances, that's generally the number that people converge upon. Neptune moves by about 5 to 10 AU. So if you had enough mass to move Neptune by 5 to 10 AU, so that would put the inner belt, say, in the 20 to 25 AU region, or the inner edge of the belt. That would imply, though, that Jupiter and Saturn's separation has increased by about 2 AU over the course of the solar system. So they've drifted apart by about 2 AU. The reason that's interesting is that if we look at the period ratio of Jupiter and Saturn today, so Jupiter's orbital period is about 2.5 times shorter than Saturn's orbital period. Now, if these two objects, these two planets, were 2 AU closer together, it means that their original orbital period ratio would be something less than 2. And so that's important because to go from something less than 2 to 2.48 today, Jupiter and Saturn would have had to cross their 2 to 1 mean motion resonance. So I just got done explaining how mean motion resonances can be sources of stability in the outer solar system. However, when you have the two most massive planets in the solar system in resonance, they could be perfectly stable, but that's actually a source of instability for the rest of the solar system because they come to conjunction at the same place over and over and over. And so you're getting this massive gravitational perturbation on the rest of the solar system while they're in resonance, and it can drive up the eccentricities of all the other planets. A simulation of this is shown here, where basically we have Jupiter's orbit in red, Saturn's orbit in yellow, one of the ice giants' orbit in blue, the other ice giant in purple, and then we have a massive primordial Kuiper belt surrounding this, just like the setup that I just described. You'll also notice that there's this dashed line, this dashed yellow line that's just exterior to Saturn's orbit. That marks the 2-to-1 resonance with Neptune. So, sorry, the 2-to-1 resonance with Jupiter. So initially, Jupiter and Saturn are closer together than their 2-to-1 resonance. Then they're going to cross it. And so we'll start this movie. I should have already started this movie because it takes a while. But as the inner edge of the Kuiper belt is eroded, Jupiter and Saturn slowly get closer and closer to that 2-to-1 mean motion resonance. But initially, because there's this gap between the planets and the primordial belt, it takes a while before you start really feeding in lots of primordial belt objects into here. But at about 800 million years in, they're going to hit their 2-to-1 mean motion resonance, and you can see what happens. Yeah, I think it's like 870, maybe. Yeah, there we go.
Oh.
So, yeah, the whole system destabilizes. And so, basically, what happens is when they hit their 2-to-1 resonance, that greatly pumps up the eccentricities of Uranus and Neptune to the point where they actually get on crossing orbits. They can scatter directly off of, when I say directly, I mean within the Hill radius of Saturn. And if that primordial belt didn't exist, one or both of those objects would be completely ejected eventually. But that primordial belt was still roughly intact when Jupiter and Saturn hit that mean motion resonance. As a result, when these two ice giants become very eccentric, their apocenters end up plowing right through that belt, and dynamical friction recircularizes them into more widely spaced orbits. And so this is an evolution of the solar system called the Nice model. And basically, we want to test these types of simulations. These types of models for the solar system? Did Neptune actually migrate by 5 to 10 AU? And if so, how violent was the process? And so what we want to do is basically track Neptune's past evolution to try to figure out. We want to use Trans-Neptunian objects to try to track Neptune's past evolution better. And so we want to do this with a combination of simulations and surveys. So again, like I said, when we look at the Kuiper belt today, it's clearly been influenced by the gravity of Neptune, and it's very consistent with Neptune having migrated outward from the sun. And when we run simulations like this, the simulations predict a given orbital distribution of Kuiper belt objects for a given model of planet migration. So different models of planet migration can give you different looking Kuiper belts. And ultimately, what we'd like to do is take simulations of the formation of the Kuiper belt. The Kuiper belt that we get out of that, we want to compare it with surveys. However, that's a problem because TNOs, Trans-Neptunian objects or Kuiper belt objects, the surveys that discover those are not unbiased. And so the orbital distribution that pops out of the Trans-Neptunian object survey depends on many things. It depends on the underlying orbital distribution of the Kuiper belt. That's what we ultimately want to test in these comparisons. However, it also depends on the underlying size distribution and the albedo distributions of these objects. So if the objects have a very steep size distribution where they're dominated by the number of small bodies, and so if they're dominated by very small, hard to see bodies, your surveys are primarily going to return objects that are very close, right on the edge of your survey's detection limit, so you're going to be very biased towards low perihelion objects. And you have to back that out. It also depends on the survey's sky coverage. So the vast majority of these surveys are not all sky. They typically look at a small patch of sky, typically right along the solar system's ecliptic. And so if you're looking right along the ecliptic of the solar system, you're going to be biased against finding high inclination objects and biased towards finding low inclination objects. In addition to that, it just depends. There's also going to be dependencies on your detection pipeline. So typically when you find these objects, you have to track them through at least 3 separate fields of observations. And so to do that, often if you're looking for very slow moving objects in the Kuiper belt, if you have something that has a rapid motion across the sky, you're going to miss it. And then of course it depends on the limiting magnitude of the survey and in general the observing conditions night to night. Meanwhile, simulations don't have any of these. They basically they're a perfectly clean data set, if we want to compare simulations with survey orbital distributions, we have to get a handle on these things. And so fortunately, people thought about this people other than me have thought about this for a long time, and I've been lucky enough to get involved with some of these surveys. The surveys that I've been involved with, or the survey I've been involved with, is known as the Outer Solar System Origin Survey, so OSIS for short. Its predecessor survey was known as the Canada-France Ecliptic Plane Survey. And so what they've done is basically every field so they have an automated detection pipeline. Every field, they embed artificial objects into that field and see how well they're recovered by their detection pipeline. And so for each field in the sky that they survey, they can come up with a plot of their detection efficiency as a function of the apparent magnitude of the object. And so basically, if you have an object from your simulation, you know its orbit, you can predict where it will appear in the sky. If you then assign it a size from a given size distribution, you can also predict its apparent magnitude, and you can predict the probability that this survey would have discovered it. So you can use this type of data to produce a synthetic data set from any one of your numerical simulations. And so we can use this survey simulator to produce a synthetic data set to compare against the real data set. And so these two surveys combined have discovered about 1,000 Trans-Neptunian objects, 1,000 Kuiper Belt objects, and this allows us to compare basically almost apples to apples when we compare simulations to it. So the types of, so this type of work has already been done, just as an example of what we're trying to do. So by looking at objects in the 3 to 2 resonance, these are called TNOs, named after the fact that Pluto's there. Work by David this morning in 2015 showed that the most successful migration scenario of Neptune to produce these Plutino objects is to have Neptune migrate from 24 to 30 AU over the course of 300 million years. However, that migration has 2 time scales associated with it. It has a fast migration, moving from 24 to 28 AU, and that's basically before Neptune, or that's before that resonance is struck by Jupiter and Saturn. So when Jupiter and Saturn hit that resonance and destabilize the whole solar system, Neptune hops by 1/2 of an AU because it has a scattering event with another planet. And then basically the migration slows down after that, and you get a longer migration as basically the leftover material after the instability gets swept up by Neptune. And just as an example of what's being done here, so basically David this morning tried different time scales for this type of migration. And if you migrate Neptune too quickly, then your simulations predict an inclination distribution of the objects in the resonance that are too low of inclination compared to the actual survey detections. And so by slowing down the rate of migration, you get a better and better match to this distribution. Oh yeah, so that's where the instability actually occurs. And in addition to that, so you'll notice right here that this migration, as I've drawn it, is very smooth. But one thing they noticed in a follow-up paper was that if the migration is very smooth, you get most of your objects from the computer simulation. So those are the blue data points. Most of the objects get piled up into resonance, and they stay in the resonance. They don't get released. Whereas if you look at the red data points, the real data, you actually get a fair amount of objects that have been released by the resonance. And what they found is that if you make the migration less smooth, then the resonances kind of bounce around and they drop objects more often. And the reason it would be less smooth is because the objects that are causing Neptune to migrate have discrete masses. So if we have one Pluto-sized object that survived this whole scenario, there should have been thousands of Pluto-sized objects early on. And so those can cause discrete jumps. Every time a Pluto-sized object interacts with Neptune, it shouldn't be a smooth interaction. It should cause, a kind of a random, not a random walk, but a guided random walk. There's probably a name for that. And so if you do that, you find a much better match to the populations of objects stuck in the 3 to 2 to the population of objects stuck that have been released from the resonances. And so again, the idea of this is that most objects, as Neptune migrates outward, most objects get carried with these resonances unless they fall out. Now, grainy migration, that's what they called that type of migration, that hoppy migration. That's one way they can fall out. But there's another way they can fall out in resonance as well. So if an object happens to be caught in resonance with Neptune, but it also happens to have a fairly non-zero inclination, something like 20, 25 degrees, what can happen is you can excite what's called a Kozai resonance, which is a different type of behavior. So in a Kozai resonance, what happens is objects oscillate in inclination and eccentricity. So the vertical component of angular momentum is conserved. As a result, when objects increase in eccentricity, when they decrease in eccentricity, when they become more circular, their inclinations increase. So during this low eccentricity phase, the object gets further away from Neptune, and Neptune has less influence on it. It weakens the resonant coupling. And so during this high inclination and high paracenter phase, high perihelion phase, objects can fall out of resonance as well that way. And so we wanted to see if those types of objects also converged on the same type of migration scenario. And so what we did is we ran 4 billion-year simulations, and we forced Neptune to migrate, just like in the previous scenario, from 24 to 30 AU, while the other giant planets were static. And we also included a disk of 1 million test particles from 24 to 30 AU, and that represented this primordial Kuiper belt, and we just forced Neptune to go through it. And so again, we had these 4 different scenarios. We had a fast migration scenario and a slow migration scenario. The difference in time scale was a factor of 3. And then we also had smooth scenarios and grainy scenarios. And we just formed Kuiper belts with each of these simulations. And so here's an example of one shown here. So we're moving Neptune through, and we're plotting the inclinations of objects and their eccentricities versus their semi-major axes. And what you can see is in resonances, objects are dropping in eccentricity. So they're becoming very circular in these resonances. This is that Kozai effect that I was talking about. When these objects become very circular, that corresponds to them getting a very high inclination as well. And so we form this nice resonant population, and the question is, if we look at these populations, how well do they match up with the real Kuiper belt? Do they agree with the same migration scenario of Neptune? And so what we really want to pay attention to is we want to pay attention to these resonance, I've heard them called Gyrs, that come down from resonances. So we want to pay attention to this population that stays further away than 40 AU from the planets. Because those objects are basically dynamically, they're isolated from the planets now. They don't undergo any strong interactions, and so they're kind of a fossil of what happened there originally. And so the question is, will those objects fall out of resonance during Neptune's migration? And that's a question of timescale. So in order for an object, let me go back here. In order for an object to fall out of resonance in one of these resonance tails, it has to undergo this type of behavior and reach this state before Neptune is actually done migrating. Otherwise, it will never fall out of resonance. So if the migration timescale, if Neptune migrates faster than the amount of time that an object can get captured into resonance and get pumped up to a high inclination and a high paracenter, then they'll never fall out of resonance. You'll only find those types of high paracenter, high inclination objects right in the resonance today, because Neptune would have finished all of its orbital action before they ever got in there. On the other hand, if the migration takes a long time, a lot longer than the amount of time for an object to get caught in the resonance and have its inclination increase, then those objects can escape while Neptune is still moving. And what you'll see, if you look at just orbits with high inclinations and high paracenters, you'll see a trail of objects that lead up to the modern location of the resonance today. And so we've measured these timescales for all of the different resonances, or all the major resonances of Neptune's orbit. And so you can see these different timescales here, and here's the different resonances on the bottom. And so just a couple, the shading here corresponds to the migration timescale of our fast migration scenario. The light gray corresponds to the migration timescale of the slow migration timescale. And you'll notice that the 3-to-1 resonance, the action happens here fastest. By the way, the air bars correspond to the 10th percentile and the 90th percentile. the amount of time it takes for an object to get caught into resonance and have its inclination and periodicity increased. But the 3 to 1 is the fastest acting resonance. And so we first became interested in that. So here's the output of one of our simulations. So this is a smooth, fast migration. So Neptune moves smoothly and moves quickly. And so if we look at the 3 to 1 resonance, so these are the objects that we're interested in. So low paracenter, which means, high paracenter, which means low eccentricity. And you can see that a few objects might have fallen out, but in general, all these objects are lined up with the 3 to 1. Now if we move from smooth, fast migration, so again, this is the area we're interested in. If we move from smooth, fast migration to smooth, slow, you can see that there's more objects that have fallen out. And the resonance itself has a longer tail. It records Neptune's migration for a longer period of time. Neptune moves slow. And so just to zoom in on the 3 to 1, you can compare these two. So we have smooth, fast migration right here, and grainy, slow migration right here. So what I'm plotting is the paracenter of each orbit in our simulation versus the semi-major axis. So here, this red line marks the instantaneous location of the resonance. The blue dashed line marks the modern location. And as we go through here, what we see is that in the smooth, fast migration, almost nothing fell out of the resonance. But in the grainy, slow migration, there's this clear trail that the resonance left as Neptune finished its migration. And so just the different colored data points here, you can see that all of the orbits that were left by the resonance, that were stranded by the resonance at high perihelion, also had high inclination. These are all inclinations bigger than 25 degrees. So there's this clear population we want to look at. And so if Neptune moves slow and not smoothly, the 3 to 2 resonance should have a significant trail of objects that mark its progression outwards. If Neptune moves fast and smoothly, there should be very few of these objects over here. Now when we look at the real objects that are known, we actually see that there are 5 objects that are clearly in the resonance and 2 that are clearly out of resonance. And if we go, so there's basically nothing out here, but there's a couple objects that were clearly left behind as the resonance continued to march outward. And so you might think, well, we're comparing, so the thing about this is I've done nothing with the survey simulator at this point. And I just looked at the Minor Planet Center catalog, and I'm just comparing data to simulations without considering observational bias. But the cool thing about this is the difference in semi-major axes between these objects and these objects is only about 5%. And so unless there's some crazy dependence on semi-major axis, survey biases aren't going to be a major problem. And the other thing about these is that they're all found, whether they're in the resonance or out of it, they're all found at roughly the same inclinations and the same paracenter values. So because we're looking at a very small corner of parameter space, survey biases shouldn't be that bad in this particular case. And so as long as your inclination and your perihelion dependence of your discovery probabilities don't change much from 60 to 63 AU, observational biases shouldn't strongly influence our ability to discern the tail population. Now the 3 to 2 or the 3 to 1 resonance isn't the only one that we were interested in though. We also looked at the 5 to 2. So the cool thing about the 5 to 2 is that you're more tightly coupled to Neptune, and the resonance is wider when objects are at high eccentricities. And so it's harder to dislodge them. So if we look at smooth fast migration, there's nothing that falls out of the 5 to 2. If you look at smooth slow migration, there's really nothing that falls out of the 5 to 2 there. However, when we switch from smooth slow to grainy slow, there's a huge amount that falls out of the 5 to 2 resonance. And so we were also interested in the 5 to 2. And the nice thing about the 5 to 2 is this has been exquisitely mapped. The boundary of the resonance has been exquisitely mapped in terms of eccentricity and semi-major axis ratio with Neptune by René Malhotra and her collaborators in 2018. These data points right here correspond to real objects that are near the resonance. So these are all real objects that are within the resonance. If we then go and look for the types of objects that we're interested in, so objects that are far from the planets, they have paracenters bigger than 40 AU, and also large inclinations, we see that there's a couple objects, one definitely in the resonance, another one right on the boundary. But if we expand our search just a little bit, we find that there are 2 other objects in this same regime that are very, very far from the resonance today. And so what you can do is you can predict where this map would have been when Neptune had a smaller semi-major axis. So as we go back in time, Neptune's semi-major axis gets smaller, so, oops. So this whole thing should slide to the left. And so for these objects to have originally reached these types of high inclinations and high and high paracenters in the resonance, originally this whole resonance map had to be located over here. So for this object to have escaped the resonance, it would have had to cross this boundary. So when it is, once they leave the resonance, they stop evolving. And so we know that when this object left the resonance, it had a semi-major axis ratio of Neptune of about 1.38. Today it does not, because the resonance has moved, Neptune continued to move outward, and the resonance has moved with it. And so today this object, 2005 CG81, has a semi-major axis of almost 54 AU. Now, if it reached its current orbit through those resonant interactions, the origin mechanism implies that this ratio, its ratio with Neptune's semi-major axis, was originally 1.384. Today it's 1.79. And so this places Neptune's semi-major axis at 29.4 AU at some point in the past. So that's not a surprise. It was less than 30 at some point, but the question is when? When was it less than 30? Well, we can actually use this plot to figure that out. So if we look at the 5 to 2, it's more slow acting than the 3 to 1. And so basically nothing gets caught in the resonance and excited to high inclinations within the first 100 million years of the solar system's history. And so what that tells us is that this had to occur, that ratio had to occur after the first 100 million years of the solar system's history. So the existence of that object at a high inclination and a high paracenter requires that Neptune's semi-major axis was at 29.4 AU or less for at least the first 100 million years of the solar system's history, and Neptune finished its migration out to 30 AU sometime after t equals 100 million years. It also predicts, if you take this and map it to the 3 to 1, we predict that the 3 to 1 tail should extend at least down to 61 AU, perhaps down to 60 AU. Currently the 3 to 1 is at 63 AU. And so the cool thing about this is this specific class of trans-Neptunian objects, high paracenter, high inclination, can provide a time resolved map of Neptune as it marches out. And currently these are pretty hard to discover. So as you can see, we found a handful of these associated with each of these resonances, but the situation will change greatly in a few years when LSST comes online. We should expect hundreds of these types of objects, if not possibly thousands, to be discovered. And so we can really map out what Neptune's done over the history of the solar system. So I have maybe, 8 minutes left or something like that. I really want to talk about Planet 9 because it's kind of fun. So another cool thing about these trans-Neptunian objects, if we go back to this map, we can also use them to probe for predicted signatures of Planet 9. So there's this idea that a Neptune-like planet orbits at hundreds of AU away from the sun. And we got the idea a couple of years ago to use this scattered disk population, so to probe for possible signatures of this planet. So most of the evidence for this planet has come from these types of objects that stay very, very far from the sun and have very large semi-major axes. But there should be an additional signature in objects that are currently scattering off of the planets. And so, again, just to show you what I mean by scattering objects, so this is another simulation, or another movie of the simulation that I showed you before. So you can see that we form the Kuiper belt, there's stuff in resonance. However, oops, hold on. For some reason, it never goes to the last frame. Oh, there should be 2 objects there. Oh, there. Okay. So, anyways, so the types of objects we're interested in right here are not the stuff that's in the stable Kuiper belt, but the unstable stuff. So these objects are currently on planet-crossing orbits, and that's why there's almost nothing over here, because they're short-lived. Almost everything that gets over there gets removed very quickly. And if we look at those types of objects, and we look at the real objects that have been discovered that are in these planet-crossing orbits that are scattering off of the solar system, if we plot their inclinations, what we see is that most of them are at low inclinations. The median inclination is 14 degrees. That makes perfect sense if they all come, if it's just, the inner edge of the Kuiper belt kind of bleeding in to the planets. The Kuiper belt mostly has moderate inclinations, so the scattering objects should have moderate inclinations. But you also notice that there's this really high inclination tail. So of the 69 known scattering objects detected by the OSSA survey, 4 of them are over 45 degrees. And 1 is even retrograde. It has an inclination of about 104 degrees. So these you cannot produce from the conventional Kuiper belt. And so this suggests that the traditional Kuiper belt can't be the sole source of these scattering objects. So to see how well this high inclination tail could be reproduced, we ran 3 sets of simulations. One where we produced these scatters with just the conventional Kuiper belt. Another where we reproduced the scatters using both the Kuiper belt as well as the Oort cloud. So the Oort cloud is this more distant reservoir that's spherical in shape, so all inclinations. So some of those Oort cloud objects can find their way back to the planets. And then we have a third simulation where we have the Kuiper belt, the Oort cloud, and one version of Planet 9 on the preferred orbit from 2017-2018. And so you can see here's the Planet 9 in these simulations. And so we'll just let this evolve in time, and you can see the difference here. So here we form the Kuiper belt. Here Planet 9 has a clear effect that's not seen in either of these simulations. And here we just have the Kuiper belt by itself, and here's the Oort cloud in this simulation. So what we do is we stop the simulation 3.5 billion years in. We look at all the objects that are in planet-crossing orbits, which I've labeled in red here, and we evolve those orbits for another 500 million years and sample their orbits, and we build up an orbital distribution. Then what we do is we take these orbital distributions from these 3 simulations, and we run it through the survey simulator, and we produce a synthetic catalog. Then we take the inclinations of that synthetic catalog, and we just plot their inclinations, the synthetic detected inclinations from each simulated system, and compare them to the real data, which is shown in green here. So the first thing is the dashed line is the Kuiper belt by itself. So the Kuiper belt by itself, you can see that it completely peters out at about 40 degrees. So here, this line marks the 45 degrees inclination right here. So you can see you basically can't use the conventional Kuiper belt to make any scattering object with an inclination bigger than 40 degrees or so, 45 degrees. Meanwhile, if we have the Oort cloud, you do get this tail to high inclinations, some even retrograde. But the tail is small. It's about a factor of 3 to, the population of very high inclination objects is about a factor of 3 too small to agree with this data set. Then you can see when we've included Planet 9, Planet 9 is amazing in making these high inclination objects, but it's actually too amazing. This strongly disagrees with the actual observed data set. And so the nominal Planet 9 model that we used, again, was what was in the literature in the 2017-2018, which is a 10 Earth mass planet, eccentricity 0.6, and a sine major axis of 700 AU. We've been able to use the scatters to rule that out completely. Just as we published this, some new Planet 9 papers came out and claimed that actually the mass should be more like 5 Earth masses. It should be in less eccentric orbit. And so we've run those simulations too, and I'll just show you right here. They're actually not a bad, so it turns out that the meat of the distribution actually disagrees pretty strongly, but it's only about a 2 sigma outlier, and the tail is a decent agreement. And so I think the takeaway here is that these scattering objects that actually come close to the sun and are pretty easy to detect can actually be used can actually be a pretty powerful constraint on the most distant part of the solar system. So I view this as there's basically 2 explanations for this long tail. The first is that the Oort cloud could be underpopulated or more populated than we expect in these types of simulations, because the formation model of the Oort cloud was pretty simplistic in these. You can actually have effects like the sun's birth cluster that enhance the population of the Oort cloud, or you might just have to turn the knobs on the Planet 9 model, and maybe we just use the wrong Planet 9 initially, and this is closer to the right answer. And so with that, I'll just, that was my last slide. So the bottom line is that, TNOs, Trans-Neptunian objects, offer windows into the solar system's past, as well as windows into the most distant part of the solar system. And so they offer constraints on both the dynamical history of the solar system, as well as parts of the solar system that we can't see, and this situation will only get better in the coming years with the advent of LSST. With that, I'll take any questions you have. Thanks. Yes.
I really enjoyed the talk, by the way.
Oh, thanks. Appreciate it.
I wanted to ask you, when you said like objects, Neptune and Uranus can fling objects inwards and Jupiter flings them out.
Yes.
Is there a connection between the asteroid belt and these objects, or is that completely separate things?
Yes. So during that, so there is. So in the smooth migration phase of that, Neptune.